Yeah.
Yeah, yesterday's session I actually didn't understand a lot.
Okay, no problem, because
Yeah, I will see the recording. I will see the recording and I will write down the topics which I don't understand.
yeah, that is okay. But the one which was discussed is a PAT exam. PAT is the physics aptitude test for getting into undergraduate physics in Oxford, Cambridge universities.
Okay.
So you are still in the 11th standard, and you just started the 11th. So you have a lot of, new topics and way of solving problem to be understood in all the subject. That is up to when you complete up to your 12th standard, you will see that you can understand many of the things what was discussed yesterday.
Okay. Okay.
Okay. Also, why I mean, you can say so. I forced you to attend that because just to see that how an aptitude test, because the guy, the Luke Scott, he supposed to be, he was a graduate from Cambridge.
Okay.
Okay, he did aerospace engineering there. So he did both his bachelor and master's degree in Cambridge University, and that means, whenever he joined, he has passed the exam. So
Okay.
the Cambridge and Oxford both they will consider the marks in the school final exam, and also they will have an aptitude test like this, and then there will be a personal interview. They will call the selected candidates for a face-to-face interview, and then in the interview also they will ask questions like mathematical questions and physics questions, chemistry, and try to make the student, whatever the subject they are learning, try to see that whether they are listening and understanding, and how they are going along with the discussion and everything. They will look into that,
Okay.
because there is something called the observation, and how we are learning things from the through the discussion, and while lecturing, when something has been told, how carefully we are looking into it and process it, analyze it, and use it for the thought process, and also how we are applying for the given problem or the situation. They will check that as well.
Okay.
And that will also indirectly, that will tell, let's say, if you are going for studies in a particular university, or you're lecturing or tutoring or lab activities like that, then they will see that whether the particular candidate is capable of joining that university and making use of the time and the resource they are spending on all the students, to use it for them and also for the rest of the society. Okay.
Okay.
So no need to worry. First of all, okay. One more thing. I'm telling a lot of things to you.
Okay.
You see, fortunately or unfortunately, we have only one brain. Okay, and we have to use that for the betterment of everything, including us. Okay, there is no point in thinking about what could not be done, and what we missed, and regrets and everything. That is actually going to be totally useless for anybody. Okay, what has happened is what has happened. Even for example, when you are solving your homework problems, or when you are studying, you missed some time, like rather than studying, you might have been spending it for going around and spending time with friends or something like that. That has happened. There is no point in thinking about it or looking into it, because that means we are wasting more time on that. Do you see that?
Yeah. Yes.
So what we got is the current present time. That is why it is called a present. Present means a gift that is gifted to us. Okay. So try to use that as best as possible. So even when you are doing an exam or a test or something like that, you might have spent some time on a problem. Use fully for that problem. make use of the information and the data provided there, and that will guide you with your already available knowledge, I mean, in and around that problem or the situation, and also you will get the full power and the capability of our brain to use for what we are doing that particular thing on the particular time. Do you get that?
Yes.
So that will actually help us to quickly get into the whatever the thing we need to do to handle the situation or the problem, and quickly solve also. And we should be alert in all possible ways to make sure we are doing it in the correct way, so that we are not, I won't say wasting, but not unnecessarily spending time on something not necessary. Do you get that?
Yes. Okay.
And we have to move on. Like we have to not rushing around, but very smartly use the time what we have. And then when we complete it or when we don't complete it, doesn't matter. We have to move on. Let's say one problem has taken more time than we planned, and maybe we could not even solve the problem. That is okay, right? Because we cannot carry on with that thought process with the next problem. That will actually jeopardize our whole capacity and capability, everything on the other problem. Do you get that?
Okay.
So don't ever think the negative thought process and all the things should be removed completely. It cannot come just like one day, I mean, somebody like me told so you can just follow it. You have to make it as an habit, practice it, train it, and then you will see that always we should be peaceful. That is very, very important. Okay, remember that. Okay, so okay, I mean, we supposed to discuss about the trigonometric function, and
Yes.
from there we plan to move something. But yesterday in the session, can you find any problem what that guy discussed that you have idea and you learned something about that, but what he discussed or from the problem you find that it was not clear for you?
There was one electric circuit question.
Okay. So can we look into that as an example
Yes.
to start this discussion? Okay. That should have been okay for your level studying in. You are doing CBSE, right?
Yes.
Yeah, you should solve that problem. Okay, this is what the given circuit was. So there was a battery. You can see the whiteboard, right?
Yes.
Okay, so the battery was separate. It was a separate second.
Yeah. It wasn't there in the diagram.
Yeah, this was a battery which was a 6 volt and 125 ohms. Right, this was
Yes.
a separate. This was the B part of the problem. But in the A part, they have given a circuit which has a node called A, and that is something looking like that. A load of one load and then another one load, and this branched into another one. Okay, and this one also branched into one, and there is a C and a D, right? Also connected, not open. They're connected, and all the way. This was connected. It is built like this. The circuit was looking like that, right? With
Yes.
all the okay, first part was, the A part was, what is the equivalent resistance that is measured or that is felt between A and B node. Okay. First
Yeah.
of all, I mean, I think straight away, as I keep saying, like what has been given, that has to help us to understand what is there. From there, we can always get the steps and the procedure to be done and followed. our understanding by the given circuit is they are all of them are 1 kilo ohm, right? All of them. Okay, they are
Yes.
equal value, 1 kilo ohm, 1 kilo ohm. So look into that. I mean, this is I find this is better rather than using the one straight away playing with the numbers. It is always better to consider that as, okay, call that as for example, as a capital R, right?
Yeah.
Okay, take it like that. And why I'm using that, because when we are playing with the numbers, like the number will simplify very quickly, and it may lead to where we started, what happened to that number, we cannot trace it out. And also all the values here are 1 kilo ohm. Which 1 kilo ohm we used, that also will be, so we can even put R1, R2. You remember last time I told you in a room temperature T1, T2, T3. Let's say these values are different values, then we could use R1, R2. Even same values, we can even start with using R1, R2, R3 like that. Okay, but let's do it with R itself, because all of them are equal. I will do it with the first thing what we need to do is, we need to understand what is this. This is a circuit and it is connected between A and B. If you use a multimeter and put it in the measurement of the resistance, it will show you a resistance value, right?
Yes.
We are asking the question, what is the RAB? That is the question. RAB equals what? The equivalent resistance, right?
Yes.
Okay. Understanding has to be, the confusing part or the one which might not be clear for many of us is which one is connected in series and parallel, because we straight away go into that, because we have been told or taught like that, if two resistances are connected in series like this, right? R1, R2. Then this can be simplified as a single equivalent resistance. Let's say R equivalent or R total. Then this we have been told that this is series connection, right?
Yes.
Series connection. Then we are saying that this can be, they say that as a formula or something that we can calculate, the RT value is nothing but the sum of R1, R2, right? Okay. In this, lot of things are going on. The understanding is very important. First of all, why this is a series connection? What is happening? Because this has to be put up in a circuit and it has to be made use of. Then we are questioning how this R1 and R2 combination connected in this way will behave, and why the necessity for making it as a single resistance value, as a equivalent resistance, and computing the value of that is sum of these two. That comes from the point that, okay, in the electrical circuits and even electronics and everything, there are some quantities which we have to understand first of all. So the voltage, right, also called a potential difference.
Yes.
Potential difference. What else the name you know for this? Can you recall? Apart from this, what else the name?
V volts per unit.
Remember the EMF?
Yes.
Electromotive force. Why I am writing all those stuff? Voltage is the name, that's okay, but the potential difference, that is actually telling something, a word like a technical word or something which you might have remembered, or you can call it from somewhere else. Where else you have heard the word potential?
Potential energy.
You see, bring back that. So that means it looks like, okay, something related to that is here, right? And it is a potential difference. Like if you take a water tank, how high is the water tank, then we are actually going to see some potential energy with the water filled in that particular water tank. Then depending on the height, and we take the water outlet as a pipe, and then the water can be distributed to different taps or whatever the pipeline connection we make. Do you see that?
Yes.
Same thing here, only difference is instead of water we are talking about electric charges stored in a battery or something like that. Then they may have a lower level and a higher level, and that is the potential difference. Do you see that?
Yes.
Okay, so next one is electromotive force, and there is another word, force. That is also, you heard, you learned everything in classical mechanics, lot of things about that, right?
Yes.
So that also something like when the electrons are moving, the charges are moving, then there needs to be a force to drive them, right? So
Yes.
if you see a battery, then let's say if you have a battery, positive, negative, then if you have a simple resistance, for example, then if there is a voltage V, we call this is the positive side of the battery and the negative, and this is a DC potential. And if there is a resistor R, something like that, conventional current, we normally consider that from the higher potential to the lower potential, the current will flow, right?
Yes.
This is understanding. So some force is actually making this current to flow. So the charges are flowing, like water is flowing. There is a force which is driving them. And what is that force driving them? Because of the energy that is available in the battery. But we call that as a voltage. So we need to understand in terms of energy. Otherwise, it cannot give that force to the charges to flow through the circuit, right?
Yes.
But the connection between the energy in the classical mechanics or in the mechanics, you might have studied the displacement, the velocity, the acceleration, and then when the mass is multiplied with the acceleration, we have the force, and the force multiplied with the distance is our work done or the energy, and per unit time, how much energy that is required to do something or store something, then we go to the power. Do you get that? Hello?
Yes, sir.
Yeah, you are listening to what I'm saying, right?
Yes.
Okay. So I was just putting a list like parallel to the classical mechanics. There is a list that we start with displacement, right? So the
Yes.
S is normally used for displacement, and we use the velocity, that is nothing but ds by dt. Have we done the differentiation already?
Yes. Just very recently.
Okay, so this is the velocity. We will discuss everything in detail, but I'm just
Okay.
want to give the analogy so that the understanding, how we build the understanding, that is actually what will help us to look into something with the information, and the understanding will always help us to solve the problem very easily. Okay, so don't just do something like has been told so I'm just doing it. That is not actually we are making full use of it. Okay. Then comes the
Yes.
acceleration, which is nothing but the first derivative of the velocity with respect to time. Okay. Already the velocity is your first derivative of the displacement with respect to time. So this will become a second derivative actually. If you have not done the second derivative, it's not a big deal, but I'm just writing it for completeness. Okay. This we call that as a, okay, all these things, they have a name. This one is our acceleration, right?
Yes.
Okay. So this is our acceleration. Now up to here in the mechanics, the mass of the whatever the object which is going through any of this has not been considered. You see, the displacement is displacement. It doesn't matter whether it's a displacement of a small ping pong ball or it is a displacement of a big planet. Do you see that?
Okay.
And what
Yes.
velocity it is moving, and when it is moving, whether some acceleration is with that and everything. But after this, if you want to make any quantity or something like that, we go for the next one is, okay, I mean there is a momentum also, that is one thing, that is mass multiplied with velocity. We call that as a momentum, right? That is
Yes.
actually multiplied by dx by dt also. That is actually our momentum. Similarly, the mass multiplied by acceleration, that we call that as a force, that will be m d square s by dt square. That is our
Yes.
force. Okay, once we gone up to here, then comes the other two. Yes, complete all of this. Then call this as the force. Normally the force is written as F, and the momentum, normally we use the because the m is used for the mass. Probably they use the T as the momentum. Okay, it depends.
Okay.
The letter. So here, when we have the force, then the work done is actually the force multiplied by the displacement. Okay, this will be our work done, also called the energy, right?
Yes.
And finally, the power, capital P, is actually equal to dW by dt. That is our power.
Yes.
This connection and the going from one quantity to the other, how to calculate them, why the calculus, the differentiation is used this way, we need to understand very clearly. Okay, we will go through that later sometime, but I'm just saying, because some of them may be straight away measurable, right? If you
Yes.
look into a small observation, like if there is a car at one point, and you can start your measurement as this is the time t equal to 0, after some 5 seconds or something, from this position, where is the position of the car, then we can measure that using a measuring tape or something like that. What is the displacement happened within the time duration of 5 seconds? You see that?
Yes.
So that is where it all starts, because some of the quantity is measurable, observable, and once we have a standard units and the measured value of that, so we have a very straightforward measurement of within a time of 5 seconds, there is a displacement of, let's say the car has moved to 200 meters. Okay.
Yes.
Okay, then we have a information. Then from there we can compute the other quantity, like straight away we can calculate the velocity. We consider that there is a uniform velocity from this point to the other point. Then that means, even though the velocity is changing, we call that as the average velocity can be calculated by the displacement divided by the time. Do you see that?
Yes.
Okay, so the 200 meters divided by the 5 seconds will give you the velocity. Acceleration can be calculated from that, like that. When you know the mass of the car, then how much is the momentum in the car? The velocity multiplied by the mass of the car will give you that idea, the quantity. Right?
Okay.
So basically we are talking about some of them are measurable quantity. Then when you measure it, we need to have a unit to standardize because I can say some displacement value. Like when I say immediately 200 meter, you can understand that, right? 200
Yes.
is a number, how to represent the 200, and meter is a unit, how much length is the meter, that is the representation of the length in a particular unit. If I say instead of 200 meter, if I say 500 yards, do you know what is a yard? Y-A-R-D, the length yard. Have you heard about it?
Yeah, I've heard of it, but I don't know its value or anything.
Yeah, because there is the British good old system, people were using some royal imperial units like, the inch.
Yes, I've heard of it. Yes.
Yeah, from the inch, even if you take the normal ruler, even now you can see on one side of the ruler you will have
Centimeters and one is inches.
Yeah, one side is the centimeter with the millimeter as the subunits. and on the other side you will have the inches, and 1/8 of the inch is called a thread.
Okay.
And the inches, 12 inches put together, we call that as a feet.
Okay. 12 inches put together is a feet. 1 foot.
Yeah, that is why we call that one particular ruler, which is a length of 12 inches. We call that as a 1 foot.
1 foot ruler. Yes. Okay.
That's the reason. And also, I mean, when we have, I mean, I don't know the answer, because they are all not in terms of decimal. Like if the standard international SI units, right? The standardized one,
Yes.
they are all in decimal. Like 10 millimeter will be 1 centimeter, 10 centimeter will be 1 decimeter, 100
Yes.
centimeter will be 1 meter, but
1
the
meter.
engineering units, they won't be in terms of multiples of tens.
Okay, so
the
hence
yard
it's
is actually,
difficult.
yard is actually when we walk. When we walk, we keep one foot.
Okay.
When we step, that one length is called a yard.
Okay.
Okay, so between that, have you watched cricket?
Yes.
Yeah, the one with the stump, the full length of the pitch from one stump to the other, I think it is 22 yards.
Okay.
So even now, I mean, when the kids play in some small grounds or something like that, they actually walk that number of steps to put the other stump.
Okay.
Okay, so that is actually in olden days we did not have any ruler or measuring tape or something. So they used the fingers, the hand, the walking distance, and everything to have this kind of measurement.
Okay.
And the yard, so many number of yards put together will become a mile. You know what is a mile, right? That is something like 1.56 kilometer or something like that. A mile. So that is how, that is another standard system. It's not a standard system, but something else was used by the humans. But we need to understand what is that. Then we can use it from one quantity, measurable quantity with some standard, with units, we know how to compute the other quantities using the mathematics.
Yes.
That is where this kind of mathematical modeling is coming into picture. So similarly, like here, why I have gone through this mechanics, simply because the voltage as this potential as like equivalent to the potential energy, and the force is there. It is something similar to that happening for the charges. Okay.
Okay.
But in reality, the electrons are flowing in this direction. Okay, remember that. That is the actual current.
Okay.
Remember that. I put the E.
Because electrons are negatively charged.
Yeah, because the protons are stuck in the nucleus, but the electrons are available throughout the material like a good conductor that can flow. Okay.
Okay.
So when they are flowing, they don't feel any friction or anything inside there. They can freely flow in the conducting wire. Okay. Simply what it is, really we call that it is flowing. It's not simply that there are free electrons available throughout the conductor. So when the negative side of the battery is connected to the material, the negative potential, this side, will actually repel the electrons in the material, in the wire. Do you see that?
Yes.
So that repulsive force is the one making the electron to flow. That is what we call as a current.
Okay.
Okay, and they won't have any friction until they move here. Okay, once they enter the resistance, the word resistance itself is saying there is a friction for the flow of the electrons.
Yes.
Right, that is why this is called as a resistance, electrical resistance, because the flow of the electron is disturbed by this resistor. Okay.
Yes.
Okay, any questions or any doubts so far?
No. Okay. No doubts.
I'm putting very detailed all over that because the understanding has to be very clear. So simply we are talking about a single resistance. So the conventional current I, because of that V, let's say this is R. According to the Ohm's law, I is proportional to V. This is Ohm's law, right?
Yes.
So one after the other, with understanding, everything will flow. Then we know that I should be equated, because mathematical modeling with equation we can go do lot of things, lot of calculation. Then we know that it needs a constant of proportionality multiplied by b, and with the unit we discuss about that, right? This side has to be so this whole thing has to be an ampere, and this whole thing has to be a ampere as well, because it is an equation. But the B alone is a volt. Then because of that, we find the K is nothing but ampere per volt.
Yes.
Right? Then only this K multiplied by V, the volt will numerator denominator go 1 to 1. Then this whole combination will become an ampere. Right?
Yes.
So this is nothing but our, with the unit of ampere per volt, will be, that is actually nothing but our 1 over R. The R itself is, because of the unit is, this is volt per ampere.
Yes.
Right?
Yes.
So that's the beauty. So now once we come to that, then we have the V equal to IR is also okay, or we have the other thing. I is nothing but V over R, or we can have
V by I is equal to R.
V by I. So why we are doing all this stuff? Sometimes these two quantities may be known, then we can calculate this. Sometimes these two quantities may be known, then we can calculate. Sometimes this quantity can be known and we can calculate. So this is what we are doing for everything. Okay, some of them are measurable, some of them are known, and from there can we do a mathematical modeling with the concept or what is happening really. Can we use that mathematical model equation to compute the other quantities, and then we can use it for some application and something like that. Okay.
Okay.
This is okay, right?
Yes.
Now let's say extend this idea. Okay, now let's say instead of one resistor, let's say there are two of them, right? So there is a one flow of current. This is going to give you a resistance of R1. This is going to give you a resistance. So there are two resistances. You see that?
Yes.
So the flow. So the previous case, when the current, the charges were trying to flow through the resistor, it was filling only one resistance. In equivalent,
now it's two.
In equivalent, you can see that when the cars are moving on the road, when there is a traffic jam, okay, that is actually giving you try to go in a particular speed, but the traffic in front of us is actually blocking us. That is giving a resistance for our flow, the movement of the vehicle. Do you see that?
Yes.
Now, same thing. The charges which are trying to flow in the electrical circuit, they feel two resistance. That is similar to in a road. Okay. Let's say when we were moving, the car could be moving with one particular jam. This is traffic jam 1. Do you see that? And when we pass to this also, there might be some other traffic jam here, right?
Yes.
So this is the equivalence of, I'm just writing an equivalence, but it is better to understand straight away in the electrical circuit. That is what is happening for our eye. But all the cars which are flowing, they will still flow. Do you see that?
Yes.
The number of cars and everything will still flow. So the I will come out here. There is no problem. So the same I, the same current is flowing through the R1. That has to. So all the number of charges, even though they feel some resistance for its flow, they will pass through the resistance 1, and then they will go through the second resistance R2 for their flow. But they will actually, all of them will come out.
Yes.
Okay. Always remember, okay, the Q is, we are all talking about the DC. That is why we write all of them in the capital letter. Okay, so the DC, electrical circuit, everything, capital letter. Capital letters, okay.
No.
Okay, because this is a simple thing for mathematical modeling. If something is constant with respect to time, we use the capital letter. Something is, if it is like velocity, we write it as a lower case because it is a function of time. Do you get that?
Yes.
Okay, so if something is changing with respect to other, in mathematics we write it in the lower case. Anything changing, we write it in the lower case. Time also, we call this is the time, but this is changing. This will change, right?
Yes.
So T is a variable. It's a variable. It will change, but it is independent variable. It is not dependent on anything, but still we have to use
Yes.
lower case.
Small letter because it changes.
Yeah, it is changing, but there is capital letter T is also available. We use this for time period.
Okay. Yes.
Okay, we will come to that later. But this T, time is a variable. This is a variable, but this capital T is a parameter. We discussed last time, right? Like in a case of y equal to mx plus c, the m is a parameter, t is a parameter. Like that, the t is a parameter. Okay. Okay. So now we know that. Do you know the charge? Let's say q amount of charge is flowing in the circuit. Q is equal to how to calculate the q?
One second. Q is equal to
current multiplied by time.
Yes, sir. IT. Yes.
Okay, so because the current is rate of flow of charges, right? Rate of flow of charges itself, yeah, Q by T. Per unit time, okay, let's say there is a conductor, this is the conductor, right? The circuit, and if the charges are flowing, okay, the electrons are flowing inside. For example, you look at that in one particular point, we are looking at, let's say, right? And we look at for one second, we observe for 1 second and count how many charges are flowing. We call that will be the current.
Yes.
Right?
Yeah.
Okay. So now, even though there are two resistors, that gives actually two resistance for this I, but whatever the charge which is flowing here, that will come back here. Right? That means the same I is flowing here also from R1 to R2. This kind of connection, the electrical connection like this, when the same current flows through both the resistances in the way it is connected, we call that as a series, electrically a series connection. Series connection. Right? This is the understanding, series connection. But you see, in the first case, let me erase all this. In the first case, we had one voltage and applied across a resistor. Then this whole, actually we measured the voltage. Voltage is actually between 2 points. So between this actually is our voltage, right?
Yes.
The current I was flowing and the R was here. Then the whole battery potential is available across the resistor. Do you see that?
Yes.
So if you measure across the voltage across the resistor will be exactly same as the battery potential. So VR, the voltage across the resistor is actually equal to the battery. So voltage across the resistor must be equivalent to battery voltage, right?
Battery voltage. Yes.
Okay, that is also, we can write it as voltage across the battery. Right?
Yes.
You see, we are saying that we know how to understand everything in the circuit. We applied a V voltage through a battery that has applied completely across a resistor, or then the voltage across the resistor is the same as the battery potential. Then we say that the resistor and the battery are connected in what kind of electrical connection? Are connected in
series.
Look carefully and tell me, what is the series here? You can say series and also parallel, right?
Yes.
Okay, series.
Is it parallel?
Yeah, it is also parallel because there is because the voltage, when the voltage is the same between two elements in the circuit, then we call that is parallel, right?
Yes.
Okay, let me draw it in a different way, and now you can appreciate that very much. Okay, so now this is the resistor. I just turned the voltage and the battery and the resistor, right?
Yes.
Look from this point. You say this is connected in parallel. Do you see that?
Yes.
So here we can say this is connected. They are connected both series and also parallel. Do you get that?
Parallel, both. Yes.
Okay. So the series and the parallel, unless the circuit gets bit more complicated or something like that, we cannot simply say that this is series or parallel. Do you get that?
Yes, it is always both.
Yeah, this is both. So the understanding has to come from that. Is what, with respect to the current, we can say it looks like it is in series connection, and with respect to the voltage, it looks like the same voltage.
Potential difference, it looks like.
Yeah, it looks like a parallel. We get that.
Parallel. Yeah. Yes.
So don't blindly just okay a circuit. Then it can be either a series or parallel. No, we need to understand what is the circuit. Then the understanding. It is not that important to name it as a series or parallel. It is more important we have an understanding about what is happening to the voltage, what is happening to the current, and what is really happening with the electron flow. You get that?
Yes.
Okay. So now in the other circuit, when we have two resistors, one here and the other one, then R1, R2. We have to use the subscript. This is a single battery potential. The current I flowing through the. So here now this getting very interesting, right? We have to say the R1 and R2 are connected in series because only series. We cannot say they are parallel because the reason being same current flow through them.
Yes.
Same current, that is a value of I, flows through R1 and R2. You see that?
Yes.
Okay. So now we know that. But how about this is the whole potential, right? The potential battery potential is available here. But in the R1 and R2, the resistance values are different. So the friction given by the R1 for the flow of the current I will be different from the friction given by the R2 because we have two different values, parameter R1 and R2 here. You get that?
Yes.
So we can separately measure a potential across the R1. We can call that mathematically, we can model that as a V1. Right?
Yes.
And we can measure separately so we can even say VR1 and this is going to be our VR2, right?
Yes.
Slowly, we don't need to blindly follow anything. Like this comes from understanding. But only V voltage was given to generate the VR1 and the VR2, right?
Yes.
Because the battery was the only having the potential, but after connecting in the circuit, R1 resistor giving a resistance of R1 value for the flow of the current I, we have a potential difference of VR1. It is the potential drop across the resistor R1, which we call it as a VR1, right?
Yes.
So first observation is the V is actually giving the VR1 plus VR2, right? You get that?
Yes.
Because this whole thing is this whole thing completely is our V, and the V is now dropped across resistor R1. That value is VR1. That should be added with VR2. Then only it will have a V. Okay. This is what is called. Have you heard the word Kirchhoff's voltage law, Kirchhoff's current law?
Kirchhoff's, yes.
Yeah, but it has to be said as Kirchhoff's.
Okay.
It is not a chop. Yeah, this is like CHO should be without the cha sound, not the like a chop.
Because over here I heard it only as Kirchhoff. And
Yeah, I know. Even I learned everything from there. This should be sound as a Kirchhoff's. Okay. Kirchhoff's voltage law. But this is a law. But a simple understanding straight away makes that to understand this, right? If there is two resistors taking the potential of the V completely, then the drop across the two should be, the sum of the drop across the two should be equal to the applied potential V. Okay.
Yeah.
Okay, but we know that simply the VR1 is nothing but the current flowing through that resistor multiplied its resistance value according to the Ohm's law, right?
Yes.
Right? And also VR2 is nothing but the same current, because it is connected in series, multiplied by R2.
IR2, yes.
Right? So this is all simple understanding what we had earlier. Then we use that V is nothing but VR1 plus VR2. Then we know that this is nothing but VR1 can be written as a IR1 plus IR2.
IR2.
Right? This is our V. All we are looking for, can we make this circuit, equivalent circuit, as the same battery, right? And can we have a equivalent single resistor, right? We call that as the R total. Apply the same potential and the same current I is flowing through this. Then in this circuit, we can straight away, we don't need a Kirchhoff's voltage law, but straight away we can say that this is actually the RT, the V is nothing but I multiplied by RT, right?
Yes.
Okay, so in this circuit, equivalent circuit, we have an equation for the V as I equal to RT. In this circuit, we have the V equal to this V can be written as I is a common multiplication factor multiplied by R1 plus R2, right?
R2, yes.
So that also we can write it here, I multiplied by R1 plus R2, right?
Yes.
So we are looking for the equivalent one. So in the both the equation, both the mathematical model for both the circuits, the V is a common one, right?
Yes.
So we can actually make the replacement that IRT is nothing but, can you see where I am writing?
Yes, sir. Yes.
Yeah, that is R1 plus R2. And we can divide by R common current both the side. That gives the equivalent resistance is nothing but R1 plus R2.
Oh, so this is how we get it. Okay.
Yeah, this is how. This is not a formula or something. With understanding and what is really happening in the electrical circuit, we could do that simply. This is very straightforward. Okay. Okay.
Yes.
Let's try to do that for the parallel one. Okay. Let's say we take a simple battery. Now we have one resistor connected, another resistor connected. They are connected in parallel. What is the meaning it is connected in parallel? The voltage that will actually, the circuit is closed, definitely a current will be coming out of that. We call that as I. But when the electric charges come over here, it see a node. It's called a node, right?
Yes.
Node, N-O-D, node. At this node, what will happen? It will branch out. Call this as the resistance value R1, this as the resistance value R2. This will branch out. Call that
voltage won't be the same in both.
Voltage will be the same, but the current will branch out. So this current I will be split into I1 and I2.
Okay.
Okay. So definitely the charge cannot stop in a node because they are all electrical circuit and good conductors. So whatever the number of electric charges which has flown here, that has to split into two. Then definitely we know that I is nothing but I1 plus I2. Okay. So this one, we call that as the Kirchhoff's current law. Okay. So the current law is actually conservation of charges. By conservation of charges, all the charges which is coming to that node, the incoming charges must be equal to the total number of outgoing charges. That is what is the conservation here.
Okay.
Right? In the case of the previous case, V equal to V1 plus V2, this is conservation of energy. So we put R1
Yes.
and R2. If you remember this one, right? This is conservation of energy. Because whenever there is a drop across the resistor, it will produce a potential difference there, the voltage across that, and the voltage is actually the potential, that is the energy, the electrical potential energy. Okay.
Okay.
Energy can neither be created nor be destroyed.
Not
That is why this one is the Kirchhoff's voltage law, and this one is the Kirchhoff's current law.
Correct.
Right?
Okay.
So simply here also we know that as you already said, now the voltage is the same. So the voltage across, so VR1 is also the V and VR2 is also our V. You see that?
Okay. Yes.
And current is different. I1 current and I2 current. Right?
Yes.
So because of this, we understand R1 and R2 are connected in parallel. Connected in parallel. So parallel. So when you have a circuit, check whether the voltage is the same between, not by numerical value, by the connection. Like the voltage is applied, the voltage is in parallelly available for the R1 and in parallelly available for the R2. That is what makes the R1 and R2 are connected in parallel. Okay.
Okay.
This is you can see that all our electrical connection at our home, we have the phase as one wire and the neutral is the another wire. Okay.
Okay.
When we attach any appliance, let's say you put a plug, a socket on the wall to get the voltage or connection, electrical power for your charging your phone, then that is actually taking the 220 voltage in parallel. Do you see that?
Yes.
And but the current is flowing in the main line. The current is actually coming, and when you connect the charger, then some of the current will get into your mobile.
Yes.
That can be seen as the voltage. The main voltage battery here can be understood like a 220 volts available for our domestic supply, power supply, electrical power supply.
Okay.
And the R1 you can think like in parallel you are driving the R1 could be the electrical load coming from your mobile charger.
Okay.
And depending on how much load is that electrical load, that much amount of current will be taken by that particular electrical load.
Okay.
Some small current will be flowing, and in the same main wall socket there may be a refrigerator or there may be a washing machine may also be connected. Do you see that?
Yes.
So it will still see that is parallelly connected. So a mobile charger is connected for the 220 volts. In parallel, the refrigerator is connected with a compressor and for cooling and everything, and also a washing machine with a big motor for rotating all the clocks and everything. So they will consume more current. You see that?
Yes.
So depending on what load, what resistance they give, they will consume so much amount of current. So you have the 220 volts as the main power supply. In parallel, all the appliances are connected. That is a circuit simply looking like this. But here we have only two loads connected, R1 and R2. Okay.
Okay.
So now we know that when they are having two different current, then we can say that the IR1 is nothing but our V divided by R1, right?
Yes.
and the other current. Okay, I put it as a R1. Maybe we can use the R also if you want. This is our R1 and this is our IR. Okay. So our IR2 is actually nothing but V divided by R2.
Okay. Yes.
Okay. So now the question is, we know that actually we are asking what is the equivalent of this one in terms of if you put one single battery, the same battery with one equivalent resistance, right?
Yes.
So now the total current I will be flowing and here V applied. So here we have the equation V equal to IRT, right?
Yes.
So in the equivalence we have V equals IRT. See, this I is the same current which is coming out of this in the circuit here also. In the circuit here also is the same I. Okay. So
Yes, okay.
with this we can rewrite that I is nothing but our V over R2.
Okay.
Okay. So we know that I is nothing but our IR1 plus IR2. Okay. So now substitute the whatever we have calculated from one circuit. I is nothing but V by RT. In the other circuit, this has to be V over R1 plus V over R2. Right?
Yes.
Now we can take the V over RT and this other side V is a common multiplication factor 1 over R1 plus 1 over R2.
Yes.
We can divide both sides by V, that will make it 1 to 1. Then
So 1 by RT will be 1 by R1.
1 over, exactly. This is also not a formula. You see, simply we derived with
Yeah.
our understanding.
Yes.
And also we can generalize if you have n number of resistor with values R1, R2, R3 up to Rn, then the equivalent resistance, the reciprocal of the equivalent resistor should be equal to the sum of the reciprocals of the individual resistors connected in parallel.
Okay.
Okay. So now comes the no problem here, right? Understanding everything.
Yeah, no
is
problem.
fine.
Yes. Yes.
Even the units can be used everywhere, and you can see that units will also follow everything. Okay. And the last thing what we have done, I just want to get you to remember this. Okay. Here, lot of students will make a mistake here. In this case, the reciprocal is the one we have calculated. You get that?
Yes.
So eventually, okay, we are looking for this is R1 and this is R2, for example, R1, R2. Then we want the equivalent to be a single equivalent resistor. We are looking for RT value, not 1 over RT.
Yes.
So mathematically, even though we have the derivation, everything like this has to be finally we need to take like 1 over RT, nothing but take the common multiplication factor. That makes it as a R2 plus R1, right?
Yes.
Then take the reciprocal. You know what is reciprocal, right?
Yes.
The reciprocal on both the sides will give you RT is nothing but R1, R2 divided by R1.
R1 plus.
Okay. That you should always remember. Many students make this mistake. They simply calculate the 1 over RT and use that as the equivalent resistance value. Once we calculated the 1 over RT, we need to reciprocal that. Okay.
Okay.
Okay. Quickly go through that particular thing. I don't know which one made you to make it difficult to understand. Here we had right? Right?
Yes.
Just to look for what is happening. Let's say the current I is flowing here. The circuit is not having that, but our understanding should make use of that. When the current comes out, it is actually splitting into I1 and I2. Do you see that?
Yes.
That itself is telling that the branching out of the current is saying this whole side is parallelly connected to this. Do you see that?
Yes.
And then when the I2 will come here, that will branch out as a I3 and I4.
Yeah.
Okay,
This
that
is
tells us
parallel.
this whole thing. Yeah, you see, it has to, our observation should help our understanding to get what it is. But the same I4 goes here. So that means this is connected in series.
Yes.
So this is a one first parallel connection, parallel, and then another parallel. You see that?
Yes.
So this
The C
combination.
and D are just a key, is it? It's just a key.
But, no, they have a second part of the question to ask the what is the current flowing. They are asking what is the I4 is.
Oh, okay.
That was the part B. That's why they put that extra C.
Okay.
You can see that as a switch. That is okay, but
Yes.
they simply want to have a CD to post the second question. Otherwise, it's only wire.
Okay.
Okay. So as this is series, we can say that this combination is actually R1. Let's say call that as a R1 equivalent, for example, the starting one, R1 total, right? That will be 2 kilo ohm, right?
Yes.
Isn't it? And that is connected in this 1 kilo ohm also in parallel. So the 2 kilo ohm is parallel with 1 kilo ohm.
1 kilo.
So this whole thing can be written as the equivalent as 2 multiplied by 1 divided by 2 plus 1.
2 plus 1.
So this is this one, right? That is the thing what that guy written as a 2 over 3 kilo ohm.
Yes.
Then that is in series with this 1 kilo ohm. So this whole thing will become 1 plus 2 over 3. That is actually 5 over 3.
Yes. Okay.
5 over 3 kilo ohm. Then this 5 over 3 is actually in parallel with this 1 kilo ohm.
This one. Yes.
So the total final one is nothing but 1 multiplied by 5 over 3 divided by 1 plus 5 over.
Yes.
Okay. So that will be 5 over 3 divided by, that will be 8 over 3.
Yes.
So that can be written as a, the 3 will cancel, it will be 5 by 8, right?
Yes.
So this is what he has written as it is 1 kilo ohm. This 5 can be written as RT is nothing but 5000 divided by 8 ohm. Okay, so this goes with 48 is 6, remainder is 2, that would be 2, 5. So this is 625 is what is calculated. Okay, once we know that, we now know that there is a 625 ohm which is connected with a battery of 6 volt, connected in series. Internal resistance is 125. And this is simple, right? They are connected in series, add them, that will help us to find what is the current. So what will be the I value? I value is nothing but 6 volt divided by 750, right?
Yes.
Okay, once we know that, now the question is we need to have a track of what is the equivalent of this whole thing. This is actually 5 over 3, right?
Yes, 5 by 3, yes.
Yeah, so that is actually, we need to remember that this equivalent one. So this was the one we are talking about. When I ampere is going, this is actually 1 kilo ohm and this is 5 over 3 kilo ohm. Do you get that?
Yes.
So that will split into our I1 and I2. So from this simple, because there are different order of the equivalent circuit. From this we can easily calculate the I1 and I2. And
Yes.
once we know the I2, then we know that that is actually having a I2 is splitting into I3, that is across 1 kilo ohm, and the equivalent, this one is
So here
2/3
it's 2.
kilo ohm, right?
Yes. So that's
Then we will calculate the I3 and I4, right?
okay. Okay.
I4 is more than enough to tell what is actually flowing in this. You don't need to
Okay.
again split, because I4 is the same amount flowing in these two, so that is the
Yes.
same current. So once you calculate the I4, our problem is solved.
Then okay.
You're
Okay.
okay with
Okay.
right?
Yes.
Understanding
Yes.
actually driving us to look into the circuit like it will be exposed like anything. It will be standing in front of us, telling everything what to be done. When the understanding is clear, okay?
Okay.
Always try to. Any questions or doubt?
No, no. I understood this very clearly.
Yeah, okay. Like this, for any circuit, it may look straight away complicated. Don't fill your mind with brain with thinking that this is going to be complicated. What I am going to do, that is actually will reduce your capacity and understanding of what is going on. Okay.
Yes. Okay.
Simply use the understanding on the given information. They have to talk with each other. That is the analysis we should do. Always do the analysis. Bring down to our basic understanding. That will tell exactly what is given. Then automatically the steps will be followed. You don't need to memorize and all. You see the Ohm's law we derived, Kirchhoff's voltage law, current law, everything we derived ourselves.
Yes.
You see that.
Yeah. Yes.
We have done the same job like the big scientists like the Ohm or Kirchhoff, right?
Yes.
Okay, be proud with that, right?
Yes.
You reinvented everything. Okay.
Okay.
We discovered. Okay then.
Okay.
Okay, keep going, and also, I mean, don't forget. You need to do that for everything what you are learning, what you are doing. Okay, develop the understanding, make the connection with a lot of things.
Yes.
Okay,
Okay.
okay then. Okay,
Okay.
Karishma, take care.
Thank you. Thank you so much. Thank you so much.
Bye.